everyone, Ms. Javner here. Today in class we are looking at the difference between Q and K. So first of all, Q is called the reaction quotient, and it's used to measure the progress of a reaction relative to equilibrium. So it's the ratio of concentration of products to reactants at any point in the reaction, whereas the equilibrium constant is only a ratio of products to reactants at equilibrium. So they're calculated the same way. So Q can still be found by taking products divided by reactants, or for our more detailed reaction, it's the same thing. Concentrations of products raised to their coefficients over reactants raised to its coefficients. The only difference is that these can be at any point in the reaction, whereas when you're calculating K, it is only at equilibrium. So here's an example I want us to take a look at. So for this reaction, hydrogen plus iodine forms two hydrogen iodides. I can write my Q or K expression here, where HI squared is hydrogen over iodine. And I have my color code here. My black squares are iodine and my red circles are hydrogen. So if we take a look, this box on the left is showing Q. And so what we do is we want to take a look at what has to happen. So again, this is maybe initial, the start of our reaction, and we're trying to figure out how do we reach equilibrium? Where are we at in relation to equilibrium, and how do we get equilibrium? So this box on the right is showing K. So this is showing equilibrium. So if I look here, I'm trying to think, how can I make this one look like this one? And one thing that's sometimes helpful is actually to calculate Q. So I can do that by taking my products. So I have one product over my reactants. So I have two hydrogens and two iodines. So Q would look something like this. So 1 squared over 2 times 2, so 0.25. I could do the same thing for K. So I have 3 products, so 3 squared over 1 times 1, so 9. So when I take a look at this, when I think about how do I make this box look like this box? Well, I need to, it looks like, break apart one of these reactants and break apart another one of these and get them to combine together to form some new products. So I need to break apart my reactants. I need to break my reactant, and form 2 more products. And if I do that, this box will turn into this box. And so I'm breaking reactants and forming products. So this is proceeding in the forward direction to reach equilibrium. We will see that this occurs when Q is less than K. If you think about them on a number line, to make Q look like K, I have to make it bigger. So to make it bigger, I have to add more products, form more products from my reactants. All right, let's look at another example. So here's another setup. So here's another spot along the reaction. And I want to figure out, how can I make this box look like this one? Well, one thing that I notice is that I have all products present. So hopefully right off the bat, we realize that if I only have products, this is going to need to go in the reverse direction to form K. And specifically, if we think about this, we can again calculate Q and K. So this one, when we think about calculating Q, I have 5 molecules of HI, and I have 0 hydrogen and iodine. So I kind of have 5 squared over 0. We know that that's not possible, but just think about this as being infinitely big. This is huge. This is all forward direction, or all products I say. Over here again, I have 3 HIs and 1 hydrogen and 1 iodine. So again, my K is 9. So when I look at this again, to reach equilibrium, I need to break apart these products. So I need to break apart 1 and 2 of those products, and I need to form my reactants. So this one, in order to reach equilibrium, is going to have to proceed in the reverse direction to reach equilibrium. When this happens, that's when Q is bigger than K. So again, if you think I'm on a number line and I plot Q greater than K, to get to K, I have to make it smaller. And so to do that, it's going in the reverse direction. All right, the last example is this one here. So again, I can look at Q and I look at K. If I calculate where Q is at here, I see that there are 3 products and 1 of each reactant. So Q is equal to 9. When I look at my K box again, K is equal to 9. So this one, nothing has to happen to reach equilibrium. We are already at equilibrium. So this case happens when Q is equal to K. So to summarize here, when Q is equal to K, the reaction is at equilibrium. When Q is less than K, the reaction goes to the right towards the products. We're forming more products here. And when Q is greater than K, the reaction is going to go to the left in the reverse direction and form more reactions to reestablish equilibrium. There are some problems that we want to think about you can calculate this as well, just like we did with counting the particles. This one is just a little bit more math heavy. So let's take a look at this example. So it says, consider the following reaction and write the reaction quotient expression. So let's go ahead and do that. So my reaction quotient expression is going to be equal to Q. It's called Q. And it's equal to the concentration of products again, so CdCl4. There's only one of them, over my reactants, cadmium and chlorine. And chlorine is, or chloride I should say, because it's the ion, is going to be raised to the 4th power. All right, so that's my reaction quotient expression, and these again are at any point in time. Part B says a reaction vessel contains 0.1 molar of the cadmium ion, 0.5 of the chloride, and 0.2 of the tetrachlorocadmate ion. So predict the direction the reaction must shift to reach equilibrium. Show a calculation. So let's actually calculate Q. Let's see where we're at in relative to K, which is 108. So again, my products, cadmium tetrachlorate cadmate, here, what a name, is 0.25, divided by my cadmium ion, which is 0.1, multiplied by my chloride ion, which is 0.5, and that one is raised to the 4th. And when we multiply this, don't forget to divide by the whole entire bottom here. So let's grab our calculator and punch that in. So when I calculate this, I get a Q of 40. All right, so we want to compare that to KEQ. So if you think of this on a number line, I have 40 and I have 108, which is K. So we want to think about how do we make Q look like K? Well, I need to increase it, which means I need to make this number bigger, which means to make that number bigger, I have to make more products. And to make more products, I have to shift in the forward direction. And if I look at that, I think on my number line, how do I Q to be K? I have to go this direction. So I have to make it bigger. I have to create more products. So this will shift in the forward direction to reestablish equilibrium. So those are a couple examples of some Q versus K. I'll post this additional video. This is a really good summary. So if you're needing a little more information, please go ahead and watch that. Thanks for watching, and let me know if you have any questions.